So, the first thing that you will notice about our prototype is how unique it looks. And the unique visual appearance was, to some degree, an objective in the project. So, a couple of features I'd like to point out right away are the heat sinks right down here, the plasma formation area right here, as well as top part of the case right here. And I'm going to go through them in that order to some degree at least. Starting it out, I'm going to explain the bottom of our prototype here. So we've got massive heat sinks, 2 on each side here, except for the back. And these heat sinks fulfill one purpose, of course, that being cooling. And they are cooling several different parts of our circuit board, which is located entirely inside of the prototype here. So it's a self-contained unit with the exception of the power supplies. Building this required the help of several experts, namely John Stieber, who not only taught us some basics of circuitry and circuit building, but also helped us actually go about building it, and was also the one who introduced us to the idea of machining our own aluminum heat sinks. So anyways, that's our circuit in there, and without John Stieber's help it would not be sitting in there, much less be functioning. So the next part of the prototype I'm going to discuss, going a little bit out of order, is the top here. So you might be wondering why we've got this big box on top of our speaker when our circuit's all at the bottom down there. But that's because the most important part, to at least some degree, of our speaker is in fact at the top. That being a flyback transformer, and it's used to ramp up the voltage to a point where we can actually generate plasma. So getting that thing functional was quite a challenge because they're somewhat antiquated technology, and this one, for example, is from a very old computer monitor, CRT. We obtained it with the help of Rich Dankert at Envision, and then through his assistance as well as that of Steve Hearns, we were able to actually get it functioning. And without it functioning, of course, the entire speaker would not work in the first place. Moving on to the last and most important part of the plasma speaker, the part that actually is generating the plasma. We have a cathode and anode in here, and plasma is obviously formed between those two things there, but that wasn't really our main problem, because after we got our circuit functioning and flyback transformer functioning and wired in, we were able to produce plasma, and we were to some extent able to play some sound through it as well. However, one of the big problems with plasma speakers that we had to solve is that they produce hazardous gases when they are operating, and naturally that's not a good thing to have happening in anything, much less a consumer product. So that ended up being pretty much the main focus of our project, was solving that problem while also managing to bring the advantages of plasma speakers to the general market. Doing so required the help of a variety of people. First of all, through our own research, we had to figure out possible solutions. Then, through the help of many experts, namely among them Jeff Smith, Jeff Reinhardt, and also Dr. Nazay Massoud and Dr. Ann Alexander, we were able to narrow down some possible solutions to the problem to what you see here in front of you today. That being 2 massive heat sinks, 1 each for the cathode and anode. And the purpose of those heat sinks is to cool the air, because if you maintain the air temperature within a certain range, as it turns out, the gases are not produced that are harmful. So we haven't been able to test it yet, but we know for sure that one of the gases is not produced because the temperature is too high for that due to visual cues, and hopefully we'll be able to explore that more in the future. More things to note with the prototype before I actually go and demonstrate it. Just some design features. We have the cathode and anode actually screwed to a solid core wire, which then goes to the flyback transformer, because it gets rather hot and there is a risk of solder actually melting if you use it there. Additionally, it's worth noting that the cathode and anode are made out of tungsten, which is quite a bit more resistant to heat than anything else that's easily available, and as a result it's quite adequate for our application here. In fact, it performs better than we need it to. Also, our heat sinks are entirely machined by us with the assistance of Thomas Alstrom, a machinist for the CUNY robotics team. So that's the basic design of the prototype, and now I'm going to demonstrate it for you.